Hello and welcome to ML with AP. The topic for today is regularization. Let's learn. But why do we need regularization? If I have to summarize it simply to overcome overfitting. What is this overfitting? Let's try to understand what is overfitting. Friends, I'm sure that you must have heard about underfitting, overfitting, bias variance trade-off. But let's try to recap this to solidify our understanding. If you see the picture on the left over here, the first diagram, the crosses, the red crosses, these are our observed data points. And we are trying to fit a best fit line through that. Is this blue best fit line doing a good job? The answer would be no. Why? Because the inherent nature of the data doesn't look linear to us. Even if we visually inspect it, it looks quadratic to us. Okay, but what we are trying to do, we are trying to fit a linear line through it, and it is not doing a good job at it. This particular condition, when we are underfitting the model, that means we are not truly mimicking the data distribution of the observed data. That condition is known as high bias. That means we are fitting a model which is too simplistic, which is not representing the data distribution of the observed data. In this particular case, the observed data perhaps is a quadratic, and we are fitting a too simplistic linear model, y is equal to mx plus c. On the other extreme, on the right side, if you see the picture, this is the same data, observed data points. The data distribution is still the same. What we are trying to do, we have fitted a very complex model over here, probably a higher degree polynomial order model over here. The data distribution looks like it is quadratic, but we have gone ahead and maybe fitted a degree 4, 5 or 10th order polynomial over here. What will happen in this particular case? This is the situation of overfitting. Why overfitting? Because it is tracing all my data points and all the noise perfectly well, right? It is going through all the data points, right? But in case a new prediction comes, or a test set, or an observation from test set, if it comes, it will not be able to generalize well. It will not, this particular model or this particular line which we are drawing will not be able to do a good job at predicting the production or in the test set data. Okay, this situation on the other extreme is known as overfitting or high variance. There is always a trade-off between variance and bias. If you try to reduce bias, the variance will increase. If you try to reduce variance, the biasness will increase. And why? Because if we are trying to reduce bias, how we can reduce bias? By fitting a more complex model. If we fit a more complex model, my variance will go off. That's why there is always a trade-off of bias and variance, or underfitting and overfitting. Somewhere in between is the sweet spot where our model performance should be good. And the central figure which you see over here, the central diagram, this blue line now is mimicking or representing the true nature of the data. Right, the true nature was quadratic, and this is representing beautifully. So this particular model is just right model, and it has the right combination of biasness and variance. Okay, let's try to understand it little more in detail. We know now what is overfitting. Overfitting, when we are fitting a complex model, when it is chasing the noise, when we are doing overfitting, okay, all those things are there. But how can we overcome overfitting? Now friends, in the very beginning I said that regularization is one of the technique through which we overcome overfitting. Okay, now let's try to see. If you see the figure on the left, what I'm trying to fit a polynomial or quadratic 2-degree order polynomial over here, and it is fitting the data right. But what if the figure on the right, the overfitting high variance situation, probably that was a polynomial of order 4, theta 4 x4, right? And that's why we are getting this weird shape of the line, right? And it was fitting. Now, if I have to convert, if somebody asks you to convert this overfitting situation to right fitting situation, right? What we have to do? See, the answer lies over here in the polynomial itself, or model itself. the model parameter itself. What we need to do to make it simpler is we have to reduce these, or we have to bring this theta 3, theta 4 either to 0 or close to 0. When we'll bring it close to 0 or 0, what will happen? Only theta 0, theta 1 and theta 2, the model parameter, it will become a quadratic equation, right? It will become a 2-degree polynomial, right? And then it will fit the data properly. So what should be our aim? To reduce the model complexity is to the higher order polynomials we have to reduce. We have to reduce their parameter or the model parameters of higher degree polynomial to either 0 or close to 0. This is one of the technique used in regularization to reduce variance. Okay, let's see. Let's try to again further solidify our understanding of bias and variance. So let's try to see that what is on the y-axis. On the y-axis we have the prediction error. What is prediction error? In case of, let's say, our linear regression, this will be mean square error, or RMS, residual mean square error, right? Or mean square error. What is on the x-axis? X-axis is model complexity. So for that, you can imagine that this is a linear model, which is a very high bias situation. On the other side, on the high side, you'll see that it is a polynomial of 5th degree, 6th degree, right? A very complex model. So this is the model complexity on the x-axis. Let's try to understand what is this green line and the red line tells us. The green line is the training error rate, right? It is the training sample data which we have projected. On the left hand side, when we'll start, because our model is too simplistic, both our training and test error will be high, correct? Why it will be high? Because we are not fitting the data properly. The data is far more complex than what we are trying to fit it with a straight line, with a very simplistic model, right? So this particular region is high bias region, right? And the errors will be high. As we increase the model complexity, as we increase the degree of the polynomial, try to understand with the degree of polynomial. If you try to increase that, right, and make it from first order to second order to third order, what will happen? Our training error rate will go down. Why it will go down? Obviously it will go down because our data is going to fit more closely, right? Our model will fit the data or the training data more closely, right? So our training error rate will go down. Test error rate will also go down. Why it will go down? Because now the model is more complex, okay? Then it has got better predictive power for the newer data sets, for the test data sets also. But something will happen if we keep increasing. Ultimately, what will happen is that our variance will keep increasing. We'll land in a high variance situation. And something over there will happen, that our training error rate will keep going down as and when we are increasing the model complexity, right? We are increasing a higher degree polynomial from 4, 5, 6, 7, 8. It will start fitting the training data more and more accurately, right? But what will happen to the predictive power? What will happen to the test or the newer observations? It will not be able to regularize well over there. It will not be able to fit well over there, right? So our test sample rate, initially it will decrease, but after a point it will start increasing. This divergence will start happening. And when this divergence start happening, that means you know that you are landing in a high variance situation, right? Where you are overfitting the model, right? When you are overfitting, the training error will be low, but your test error will go high. This is the marker of a high variance overfitting situation, right? Somewhere between the high bias situation and high variance situation is the sweet spot, right? You see this U shape? The minima of this will be the sweet spot. So whatever model complexity which we are able to achieve at this point would be the right model complexity for our model. Okay, so friends, I hope this bias variance trade-off is clear with this particular diagram. Okay, now let's see further. Now what is regularization? Now we have already understood that what is the need of regularization. But what is regularization? In a formal definition term, it is an additional criteria which we add to the loss function to make sure that we do not overfit. Now break it down. What is the loss function? Every a machine learning model will have a loss function which we have to optimize, or we have to minimize, rather we have to minimize. And when we bring it to the minimum, at that particular minimum, whatever is the model parameter is the model parameter of our model, right? Correct? This is the standard way, whether it's linear regression, SVM, logistic, anything. This is the way it works. We have to define a cost function or a loss function. That is the loss function. Now regularization, it is saying that you have a default loss function for a particular algorithm, but we are adding a criteria and an additional criteria also, right? What is the job of this additional criteria? Is to prevent the model from overfitting, from going into the high variance situation. Okay, it is called regularization since it tries to keep the parameters more normal or regular. It tries to tone it down. Think it the term that theta 3, theta 4, or x to the power 3 or x to the power 4 parameters, right? The coefficients, right? It will try to bring it close to 0 or near to 0, right? It is toning it down. Okay, now how do we represent that? How do we like mathematically represent that, right? Regularization. But before that, regularization is a generic term, right? In case of our classical machine learning models, we use this type of regularization. Now regularization can happen in various ways also. Now in our previous videos, we were discussing about random forest or decision tree. The pruning of decision tree is also a form of regularization. It is anything which prevents a model from overfitting is a regularization technique, right? In case of neural network, sometimes there is a dropout technique. Sometimes what we do in the neural network, in a fully connected neural network, we drop out certain neurons, right? We make it dark, go. That dropout also helps in regularization, right? It prevents from the model landing in a situation of overfitting, right? So there are various methods of regularization. We'll particularly deal in the context of classical machine learning and especially on the L1, L2 and elastic or Ridge, Lasso and elastic regularization, right? Now coming back, we are talking about the extra criteria, right? This is our loss. Like this loss could be any loss, right? In case of linear regression, it will be mean square error, right? Or RMS. This is the standard loss. In case of logistic regression, it will be log loss, right? This is the extra criteria which we are adding with a lambda parameter, with a parameter called lambda. And this is a function. What is this function of? This function is of the weights and biases, right? This is the function of weight and bias. And we are putting it a lambda. So this is the extra criteria which we are adding into the overall loss, right? So this was my original loss. Now this becomes the overall loss. And what is the goal of any machine learning model? To minimize the loss. So that's why we are putting argument. So the minimum of this function, minimum of this overall thing, whatever that is, the weights and the biases corresponding to that minima will be our model parameter, right? That is a standard way how we deal with this, right? Now let's see over here. Yeah. So just try to solidify our understanding on additional criteria, right? So this is the penalty term, lambda, right? Which we are saying. So our initial will be loss, and this loss could be RMS or MSE, anything, right? What we are trying to do is this particular loss, and we are adding a lambda parameter, right? And then we have a function which is our weights and biases, right? Which we are calling weight and biases. So we are trying to add an extra criteria over here, and this lambda can be any value between 0 to infinity. We'll just see it in a minute that what we mean by that. Okay. Now let's go back to the deck. Now let's try to intuitively see that what is the impact this lambda will have. Now we know that we are adding a lambda right over here and with a sum function, but what is the impact it will have? Let's say in this particular figure, this blue line which you see is the target, right? These are the observed data points, the circles. The blue is the target, right? The blue is like the target or the inherent nature of the distribution. This fit is our dotted line. Okay, let's say our lambda is very small. Our lambda is very small. Lambda 1 is very small figure. That means What we are doing? We are not putting any penalty. This thing is effectively a penalty term, right? We are not putting any penalty. We are letting the model do overfitting. If we do not put any penalty, the model will overfit, will land in an overfit situation. And you can see with the curved line, right, this dotted red curved line, that we are landing in an overfit situation. Suppose we tune the lambda to lambda 2, we increase the value of lambda. What will ultimately happen? Our model will start going from overfitting to best fit situation, right? So it will try to mimic the total, the true data distribution over here, okay? And it will, the overfitting situation will come down, high variance will come down, model complexity will come down, the higher order polynomial will start approaching 0, right? So it will start fitting like this. If we further tune, if we keep increasing this lambda, right, then it will further increase the bias. We have started landing into a high bias situation. If we further increase the lambda, we'll ultimately land in a very high bias situation. This particular situation where we are ultimately landing a straight line. A straight line means that our model is only taking the intercept term, right? So in case of linear regression, try to think like we have beta 0 plus beta 1 plus beta 2, right? Or beta 3. How many features, that many betas will be there, right? If we set a very, very high lambda value, what will happen? All our model parameters, beta 1 to beta p, whatever is that, they will all approach 0, right? That's what model will do or the optimizer will do. It will set all the betas to 0. What it will not set? The beta naught, the intercept term, it will remain. So this horizontal line which you see dotted, it will become my beta naught. So for every prediction, this will go into an underfitting high bias situation. For any prediction, you ask a data point here, it will do the prediction as a straight line, right? Whatever y value is over there. So this is the impact of lambda. From a smaller lambda, that means we are not penalizing enough for overfitting to overcome overfitting, right? To a very high lambda, that means we have penalized a lot more. The good lambda value lies somewhere in between, and that usually is arrived from a cross-validation exercise, right? For different use cases, different data sets, lambda could be different, right? Okay, let's try to understand that how it works. Now this is a multilinear regression, right? Yeah, so y is equal to, this is a linear regression of multiple parameters. So we have, let's say, p parameters. So beta naught, beta 1 x1 to beta naught xp, right? This will be our running example case. What will be the RSS? RSS is nothing but residual sum square or mean sum square, right? What it will be? It will be yi minus beta naught, the intercept term, minus beta j xij, the whole square, right? Why it will be? Why it will be like that? Let's try to see. Okay, over here. Now this was my y, this is my x, right? Let's try to see it in just 2 dimensions so that we can understand, right? What is our residual? This is, let's say, our best fit line. The residual is the distance between this. This is our residual, right? This is our residual. Our loss typically is yi minus yi hat, right? Yi hat is this value. This is yi hat. This is yi, the whole square. This is mean square error loss, right? And we sum it for I is equal to 1 to n for all the values, right? For all the observations. This is our loss function, correct? Now this loss function, we can also, now what we are fitting? We are fitting our yi as a straight line, right? So my loss will become ultimately, let me write, loss will become ultimately summation yi minus beta naught plus beta 1 xi, right? The whole square. What is the line of the equation? Beta naught plus beta 1 xi, right? This is my equation of the line, right? And this beta naught is the intercept term. Beta 1 is the slope of this, right? Of this line, correct? And this will be from I is equal to 1 to n, right? This is what my term will be. And after that, if we include a penalty term, then it will be lambda beta 1 right? Some function of beta 1 we have not yet defined, but some function of beta 1 will be there as lambda. Okay, I hope this is clear, right? Now, what is this second summation? This second summation is nothing but for all the features. So think it like, for one, I have given the example beta 1 xi1, right? For second feature, it will be j will range from j is equal to 1 to p. P is the number of feature, n is the number of observations, right? So ultimately, we have to calculate this for one feature, right? For all the features for one observation, and then sum over all the observation. This is how MSc RSS works, right? Pretty standard. Now what we are doing, we are adding a term over here. We are saying that we add an extra criteria. This is the extra criteria which we are adding, lambda, and we are adding it's a very simple function which we are adding. We are adding beta j the whole square, and j is equal to from 1 to p, right? Now friends, couple of things. This thing is our standard MSc, right? Or RSS. So RSS plus penalty term. This is my penalty term, and what I'm applying? I'm applying the square penalty, like beta j the whole square, and sum over j is equal to 1 to p. Correct? Understood? Okay, let's see. Okay, let's go over here one more time so that we can see this with an example. Okay, now let's see. This is what we are talking about, right? My loss, and loss will be what? A function of beta 0, beta 1, beta 2 till beta p. Right? It's a function of that. MSc, we already know what is the MSc. And lambda, j is equal to 1 to p, beta j the whole square. J starts from 1. We are not putting penalty term inside beta naught. So intercept we are exempting. Okay. So that's why there is no beta naught. There is only beta j the whole square. What was our original loss? Original loss or MSc is this particular thing. Correct? Sigma or summation I to 1, n is the observation, yi minus beta 0, beta 1 xi 1, beta p xi to the power superscript p the whole square. This should be my loss. Correct? My MSc. For pth feature, okay, what will be the, let's say for pth feature, what will be this term, this lambda term over here? For pth feature, if you expand this particular thing, right? You expand this particular thing over here, right? One of the term will be beta p square xi p square, right? One of the terms will, because this is quadratic, one of the term will result like this, correct? And from over here, my lambda is what? This thing is nothing but lambda beta 1 square plus beta 2 square plus beta 3 square till beta p square, right? This is what summation means, right? From 1 j is equal to 1 to p. So there will be one term corresponding to pth feature like this from the MSc loss, and like this from the penalty, right? Correct? This figure will be there inside our loss, right? Now try to see that intuitively try to see that if my optimizer, let's say gradient descent or any optimizer which we are using, what it will do. Okay, when lambda value is 0, right? If I set lambda to 0, this whole term becomes 0. Then my loss is just MSc. So this is nothing but our standard linear regression, or what we call OLS, right? Standard linear regression, right? If lambda is infinity, if lambda turns to infinity, what will happen? This figure will become very high. Now, what will be the option in front of optimizer to lower the loss? If this thing is very, very high towards infinity, this thing has to approach 0, right? To make this overall quantity 0 or near to 0, or to minimize this, right? So the point I'm trying to make, the higher lambda will go, the lower beta will start moving on. They will go in the opposite direction. And why? Suppose lambda is in between 0 to infinity. What will happen? Let's say lambda is 0. This becomes only OLS, right? A standard linear regression. Lambda becomes 1. It will try to put some penalty for this, right? So my beta my beta j, all the beta j's will start decreasing, right? If the lambda becomes very, very high, what will happen? This beta j becomes very, very low. It will start becoming very, very low, right? So they will both go in opposite direction. And how lambda is chosen? Lambda is chosen using cross validation. There is no perfect value for lambda. You choose the penalty based on the cross validation. Let's take the example of p is equal to 2. Just to understand, we should only have two features. And those features are, the model coefficient parameters are beta 1 and beta 2. So my p is set to 2 now here. P is set to 2, right? That condition. What will be my RMS loss? My RMS loss is this, no problem. Including penalty, what will be the RMS loss? This is my standard RMS loss. This is the penalty. Penalty will be lambda beta 1 square plus beta 2 square, correct? No penalty on intercept. If you notice, we are not including this beta naught term. Friends, I keep telling this beta naught term, there is no penalty on that, okay? If we expand this particular thing, our initial MSC loss, right? If we expand this thing and expand this particular penalty term, what it will become? It will become something like that. yi square, beta naught square, beta 1 xi square, beta 2 xi square, plus there will be some term which will be combination of beta naught, beta 1, beta naught, beta 1, yi, some combination. But there has to be the term like this. These quadratic terms will be there inside, right? Because this is quadratic. A plus b the whole square. Similarly, I am expanding it that way. And then we have lambda beta 1 square plus beta 2 square. For lambda greater than 0, if we have to minimize above loss, what will be the impact on beta 1, beta 2? If we have to minimize this whole thing we have to minimize, okay? And lambda is greater than 0. That means we are adding a penalty term here. What will be the impact on beta 1, beta 2? It will go down. The beta 1, beta 2 has to go down. Our optimizer will make it go down, right? To minimize the overall equation. This is the basic intuition behind L1, L2 regularization. Okay? Now let's go back over here. So friends, I hope you understand the relation between lambda and betas, right? And this how this penalty term is acting. This penalty term, the higher the lambda, the smaller the betas, right? So I am toning down my betas. Now regularization or regularizers, right? How we call it. This is the standard equation which by now we have understood. Generally, we don't want very high weights. By weights, we means model coefficient, these betas. We do not want very high beta. Why we do not want high beta? If suppose there is a high beta, that means any small fluctuation in the feature which is related to that particular beta. Every beta is related to a feature. This is the model coefficient. Every beta is related to a feature. If there is a small change in that feature, it will result in a very large change in prediction, right? A small change in beta will result in a large change in prediction, right? You can understand that, huh? Okay. Also, what will happen is that if a particular beta is very high, what will happen? Then that means it will outweigh all my other betas. In other words, one feature will outweigh all the other features. That's why regularization is important. In mathematical terms, if we have to see, the reason why regularization is important, if we do not regularize, then let's say one parameter is very high, one model coefficient is very high, one of the betas is very high. Any change in that particular feature will result in a huge change in my overall prediction. That's one. Second, that particular parameter will outweigh all the other parameters. That particular feature will outweigh all the other features. The third thing is, sometime I've shown you in the initial beginning, right? Sometime we need to bring the weights to zero for the features which doesn't matter. Not every feature has equal predictive power, right? Some feature will have more predictive power, some feature will have less predictive power. To make the model simpler, reduce the complexity, reduce the variance, we have to reduce the number of features also. When we reduce the number of features, one way to do that is that feature which is not contributing much in explaining the model, you bring it down to zero. The feature which is not contributing enough, you bring those things down to zero. It will have a small penalty on your overall prediction power also, but that's fine. It will result in a much simpler and better model. Okay, so these are few of the reasons, mathematically speaking, why regularization is important. How do we increase small weights? How do we penalize large weights? So the overall thing is that you have to penalize large weights, right? So there are two types of regularizations which we'll initially talk. There are three which I am going to talk: L1, L2 and elastic. L1 loss is called also lasso. L2 loss is also called ridge. The elastic is a combination of L1 and L2. We'll just talk about that, what is L1, what is L2, right? We'll try to understand that. But intuitively try to understand, in the L1 penalty, in an L1 loss or the lasso, the penalty is our first order, right? The first order is the modulus of all beta j's, modulus or absolute value of all beta j's, right? So our MSE or RSS is there plus lambda. This is our total combined loss function for L1 regularization. Initial loss plus lambda j is equal to 1 to p beta j. Okay, this is our overall loss. Sum of the squared weights. Okay, now L2 loss is what? Lambda beta j the whole square. Okay, this is the penalty which we are adding, lambda beta j the whole square. This is called ridge regression or ridge loss, right? Or L2 loss. We'll try to see that why it is called L1 and L2. But the primary difference between L1 and L2 is that here we are taking the first order absolute value, here we are taking the square. Now let's see what is this norm thing which we are talking about. Okay, this norm thing. Okay, let's try to see that we have two. This is the model and we have two parameters only, beta 1 and beta 2. Suppose we have arrived at a model parameter, we have arrived at and there is a data point which is beta 1 and beta 2, and this is our initial predicted, we minimized our loss and we arrived at that figure. Okay, so this is the point over there. Just two features and a data point in a Cartesian plane. If suppose we have to measure the distance, that what is the distance of this particular point beta 1 beta 2 from origin, what are the ways in which we can calculate the distance? The first thing which comes to mind is that you go beta 1 cap distance this side and you go beta 2 cap distance this side, right? You go from here to here and you reach from here to here, right? What it will be? This distance will be nothing but beta 1 absolute plus beta 2 cap absolute, right? This is the distance I'm traveling. Since this is distance, I'm putting it in modulus or not modulus, absolute form, right? Because I just need a scalar positive quantity. So this distance plus this distance I'm going, right? And I'll represent it like this. This is one way of doing. This is the primary thing which is called L1. This is the L1 norm. We'll just see that what is norm, but this is called L1 norm or the Manhattan distance. Manhattan distance. Why it is called Manhattan? Because there are in the Manhattan city there are blocks and all, and the roads are all perpendicular to each other. So the taxi will go only, or if you have to travel or car or taxi, it will only go like this and this. Sorry, let me just erase this. Yeah. It will only go in this direction and this direction. Like in any city, you go in the perpendicular directions, right? From one street to another street, one block to another block to avenues and all. That's why it is called Manhattan. Euclidean. What is Euclidean distance? Now, from your basic coordinate geometry, you would be knowing that the shortest distance would be this, right? How do we do that? From our coordinate geometry, we see that beta 2 minus 0 the whole square under root. This is the distance, right? This is the distance. This is called our L2 distance, okay, or Euclidean distance, L2. So L2 distance is beta 1 whole square plus beta 2 whole square root, right? This is our L2 distance. Our pth, similarly, this is the L1, this is the L2. Similarly, there will be a pth norm also, right? The pth norm in a multi-dimensional space you can visualize, which will be beta 1 to the power p plus beta 2 to the power p under root of p, right? So this is the more generalized form, right? This is the square root. If you take it to the pth order, right, this is the p norm, okay? This becomes the p norm. Okay, so this is the intuition behind your norms, Okay, and then how the notation works, the L1 notation or the Manhattan distance is measured at, you always represent it with 2 bars and 1. If 1 is written down, that means it is L1 norm. If 2 is written, that means it is L2 norm. That's mean you have to do the quadratic. If P is written, that means it is Pth norm. That means it is beta to the power P under root P, right? This is this particular figure, right? So this is the representation which mathematicians have come. I do not know why, but you have to enclose it into 2 bars and you have to represent the P. So wherever you see underneath subscript written 1 or 2, that you immediately will understand this is first norm or second norm, or L1 norm or L2 norm. Okay, so this is on the norm side. Okay, with this I think we have come to the end of this video. I'll see you all in the next video where we'll be discussing regularization in much more detail. We'll try to also code using scikit-learn. Till then, have a great day and bye.